In the grand and beautiful story of the cosmos, stars are the universe's ultimate powerhouses. They take the simplest atoms, hydrogen, and under immense pressure and heat, they fuse them together to create helium. This process, known as nuclear fusion, releases an extraordinary amount of energy. It is the very same process that warms our planet and gives us light. For decades, some of the most brilliant minds on Earth have been trying to replicate this stellar magic, to build a miniature star right here on our world. The goal is to create a source of clean, safe, and virtually limitless energy that could power our future without harming the planet. On February 12, 2025, scientists in France took a monumental step towards making that dream a reality. At the French Alternative Energies and Atomic Energy Commission, or CAA, Research Center, a remarkable machine called the West Tokamak achieved something truly special. For an incredible 1,337 seconds, just over 22 minutes, it sustained a super hot cloud of hydrogen gas, known as a plasma. This achievement shattered the previous world record for plasma duration, proving that we are learning to control the very forces that power the sun. This isn't just about breaking a record. It's about demonstrating the stamina and stability needed for a future fusion power plant. It's a profound statement that we are getting closer to mastering one of the most fundamental processes in the universe, a process that could solve our energy needs for generations to come. The quest for fusion energy is one of humanity's most ambitious scientific endeavors. Unlike nuclear fission, the process used in today's nuclear power plants which splits heavy atoms, fusion joins light ones. This fundamental difference is what makes it so appealing. Fusion reactions do not produce long-lived radioactive waste, and there is no risk of a meltdown, as the reaction would simply stop if control were lost. The fuel, derived from water and lithium, is abundant across the globe. Imagine a world powered by the same clean process that makes the stars shine, a world where our energy supply is secure and our environment is protected. This is the incredible promise of fusion, and the recent news from France shows us that this promise is becoming more tangible every day. This breakthrough is a beacon of hope in a world grappling with the urgent challenges of climate change and energy security. It tells us that through collaboration, ingenuity, and a deep curiosity about the universe, we can solve the greatest problems we face. The 22-minute plasma pulse is more than just a data point on a chart. It is a chapter in our ongoing journey to understand and harness the laws of nature for the betterment of all humankind. It represents a significant stride forward, bringing the distant dream of a fusion-powered world into sharper focus and inspiring a new generation of scientists and engineers to continue this magnificent quest for a brighter, cleaner future for everyone. To truly appreciate what the French scientists accomplished, we must look inside the machine that made it possible. The West Tokamak. The word Tokamak comes from a Russian acronym that means toroidal chamber with magnetic coils. You can think of it as a hollow, donut-shaped container wrapped in incredibly powerful magnets. Inside this chamber, scientists inject a small amount of hydrogen gas. They then heat this gas to unimaginable temperatures, in this case, around 50 million degrees Celsius, which is more than 3 times hotter than the core of the sun. At these extreme temperatures, the hydrogen atoms are stripped of their electrons, transforming the gas into an electrically charged state of matter called plasma. This is the fiery fuel for fusion. The real challenge, and the genius of the Tokamak design, is how to contain this impossibly hot plasma. No physical material could withstand such temperatures, so the plasma would instantly melt any container it touched. This is where the powerful magnets come into play. They create an invisible magnetic bottle that suspends the swirling, superheated plasma in the center of the chamber, preventing it from touching the reactor walls. To sustain the record-breaking 22-minute pulse, the team at West had to master this magnetic confinement with exquisite precision. They carefully injected 2 megawatts of heating power into the plasma, maintaining its temperature and density, while ensuring the magnetic cage remained stable and strong throughout the entire duration. A crucial component in this long-duration experiment was the diverter. This is essentially the reactor's exhaust system, responsible for safely removing heat and waste particles, like helium ash, from the plasma. In the West Tokamak, the diverter is made of tungsten, a metal with an extremely high melting point. Running the reactor for 22 minutes placed this component under immense stress, but its successful performance was a key part of the achievement. It demonstrated that the materials and design choices were robust enough to handle the grueling conditions of long-pulse operation. This wasn't just about keeping the plasma hot, it was about proving that the machine itself could endure the marathon. This French achievement stands on the shoulders of decades of global research and provides a crucial piece of the fusion puzzle. While other experiments have reached higher temperatures or produced more energy in short bursts, the West record is all about endurance. For example, the JET facility in the United Kingdom set a record for energy output in 2024, producing 69 megajoules in just 5 seconds. Meanwhile, China's East Tokamak previously held the duration record. The French success adds a new dimension, proving that steady, controlled, and long-lasting operation is achievable. It's like learning not just how to start a fire, but how to keep it burning steadily and safely for a very long time. In the world of fusion research, there are different kinds of records, each important in its own way. Some experiments, like those at the National Ignition Facility in the United States, have achieved net energy gain, producing more energy from a fusion reaction than was put in to start it. This is a monumental scientific milestone, like a sprinter breaking the 10-second barrier for the first time. It proves that the fundamental concept works. Other experiments, like the United Kingdom's JET, have focused on maximizing the total energy produced in a single powerful burst. This is like a weightlifter setting a new record for a single lift. But the French record at West is different. It's not a sprint, it's the beginning of a marathon. For a fusion power plant to be practical, it can't just operate for a few seconds at a time. It needs to run continuously, day in and day out, to provide a steady and reliable supply of electricity to the grid. This is why long-duration experiments are so incredibly important. Running a plasma for 22 minutes is a massive step towards demonstrating this steady-state operation. It forces scientists to confront a whole new set of challenges that don't appear in short-pulse experiments. It's one thing to hold your breath for 30 seconds, but quite another to run for 30 minutes. The latter requires control over breathing, pacing, and endurance, which are exactly the kinds of challenges faced in long-duration fusion. One of the biggest hurdles in long-pulse fusion is managing the immense heat and particles that escape the magnetic cage. Even with the best magnetic confinement, some energy will always leak out and hit the inner walls of the reactor. Over a long period, this can cause components to heat up, erode, and potentially fail. The West experiment was a critical test of the reactor's skin, the tungsten diverter, and other plasma-facing components. Its success in handling the continuous bombardment for over 20 minutes shows that we are developing materials and engineering solutions that can withstand the harsh environment inside a future power plant, ensuring both durability and safety over long operational lifetimes. Furthermore, maintaining a perfectly stable plasma for an extended time is an incredibly complex balancing act. The plasma is a turbulent, dynamic entity, and small instabilities can quickly grow and cause the reaction to fizzle out, an event known as a disruption. The scientists at West had to develop sophisticated control systems that could monitor the plasma in real time and make tiny adjustments to the magnetic fields and heating power to keep it perfectly balanced. Achieving this stability for 22 minutes is a testament to the maturity of our control strategies. It builds confidence that we can tame the stellar fire and operate a fusion reactor not just powerfully, but also reliably and predictably. The success at the West Tokamak is not just a standalone achievement. It is a vital stepping stone for an even grander project being built just a short distance away in southern France. ITER, the International Thermonuclear Experimental Reactor. ITER is a massive international collaboration designed to be the world's largest tokamak. Its goal is to demonstrate the scientific and technological feasibility of fusion power on a grand scale, aiming to produce 500 megawatts of fusion power from just 50 megawatts of heating power, a tenfold energy gain. The lessons learned from West are directly applicable and invaluable for making ITER a success when it begins its own operations. Think of West as a brilliant dress rehearsal for the main performance at ITER. Every piece of data gathered during the 22-minute run provides crucial insights. The experience gained in managing the tungsten diverter, for instance, will directly inform how operators will handle the even more powerful heat exhaust systems at ITER. The advanced control algorithms developed to keep the plasma stable for such a long duration at West can be refined and scaled up for use in the much larger and more powerful ITER machine. By testing these components and strategies on a smaller scale first, scientists can de-risk the operation of the multi-billion-dollar ITER project, ensuring it can achieve its ambitious goals safely and efficiently. Of course, significant challenges remain on the path to commercial fusion energy. We need to develop materials that can withstand neutron bombardment for years, not just minutes. We must perfect the closed-loop system for breeding and handling tritium, the radioactive hydrogen isotope used as fuel. And we must continue to improve the energy efficiency of the entire system to ensure that a future power plant can produce more electricity than it consumes. However, each milestone, like this French record, chips away at these challenges. It provides the knowledge and the confidence needed to tackle the next set of problems, bringing us incrementally closer to our ultimate goal. The journey towards fusion energy is a long one, but breakthroughs like this illuminate the path forward. They remind us that what once seemed like science fiction is steadily becoming scientific fact. The 22-minute plasma record at West is a powerful symbol of human ingenuity and our relentless drive to build a better future. It moves us one step closer to a world powered by clean, safe, and abundant energy, the same energy that powers the stars. With continued investment, international collaboration, and the brilliant work of scientists and engineers around the globe, the dream of harnessing a star in a bottle may well become the reality that powers our civilization for millennia to come.